Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to look at section 1.1, which is Introductions to Linear Equations. So let's get started. All right, let us begin by looking at the objective for this section. So at the end of this section, you should be able to tell which equation is linear and which equation is not. And you should be able to solve a system of two equations in two unknown and be able to understand the geometrical interpretations of solving system of linear equations. All right, so let's look at what equations are linear. So this is equations with two variables, x and y, and we say that this equation is linear because it does not involve any products or roots of the variables, and all these variables occur at the first power and do not appear as the argument of a trigonometric, logarithmic, or exponential functions. So because of that, you can see that this is actually what we call nonlinear equations. And when you're putting all the equations together to form systems, this is what we call a system of linear equations, and this is what we call a system of nonlinear equations. So in this course, we are going to look at how to solve a system of linear equation like this. So in this particular system here, we have n unknowns. These are the unknown variable, x1, x2, all the way to xn. And we can see that we have m equations. This is the first equation. This is the second equation. So altogether, we have m equations and n unknowns. All right. And we will learn how to do that in the other section, section 1.2. One methods, one systematic way of solving a system of linear equation like that is what we call Gaussian eliminations, and we will do that that particular section. So right now we are not going to be so ambitious. We are going to concentrate on solving a system of equation two unknown, and that is two equation right here. So we have two equation and two unknown, and we want to find the solutions that satisfy both equations. So we are going to write this equation right here as this, and this equation right here as this. So this is writing it in the form of mx plus b, and from high school algebra, you know that this is the slope and this is the y-intercept. And as you can see right here, y equal to x minus 2 is going to be a straight line like this, and y equal to minus 2x plus 6 is going to be a straight line like this. And we haven't verified that yet, but you can verify yourself that x equal to 8 over 3 and y equal to 2 over 3 is this intercept point for this two line, and this is going to be our solutions for this system of linear equations. So when you are asked to solve a system of linear equations, your job is to identify the x and y that satisfy these equations and also this equation. So you want to find x and y that satisfy both equations. So geometrically speaking, what you are looking for the coordinate of the point where the two lines intersect each other. All right, so this intersection point, the intercept point, this particular coordinate here is the solutions for this linear system. And another very important thing is that it's very tempting to say that these are the two solutions for this system of linear equations, but we won't say that this is two solutions. This is in fact our unique solution. So we write them as our coordinate, 8 over 3 and 2 over 3, and this is our unique solution. So this is the only solutions that we have for the system, and this is our unique solution. So there's only one solution for the system of linear equations, and that solution is given by this. So this is the x coordinates, and this is the y coordinate. All right, let's look at the second example here. So in this second example, we have the system of equations. And again, you look at this. This is line y equal to x minus 1. And this is a line y equal to x minus 2. So they have the same slope and different y-intercept. So you can see they can be represented like this. And if you are looking for the point that will be satisfied by both equations, you will see that that's not possible in this case. So in this case, we say that the system does not have a solutions, or the system is inconsistent. So you're looking for the intersection point. You know that the two parallel lines on a plane will not intercept, right? So they will not intercept each other. And if you're looking for that intersection point, you will see that that intersection point will not exist. So the system is inconsistent, all right? So that's an easy case. There's no solution for the system of equations, linear equations. And now we are going to look at another situation, the third example here, where you are given two equations, but you immediately realize that the two equations is actually the same equation. So if you're looking at the line, so this is y, this is x. So this is y equals to 1 minus x. So this is going to be a line like this. And the other ones, 2x plus 2y equal to 2, is also the same line. So these two equations, if you draw the line, these two lines are intercepting each other. These two lines are overlapping each other. So basically, every point that is on this line will be a solution for the system of equations because they are the same line. So every point that is on this line, every point right here that is on this line will be the solution for this differential, for this linear equations, not differential equation, but linear equations. Okay, so immediately you will see that we have infinitely many solutions. And the question now is, how do you write down all the solutions? So for example, there are many solutions. So let's say that I choose my x equals to 0. If I choose my x equal to 0, my y will have to be 1. If I choose my x is equal to 1, and then my y will have to be 0. If I choose my x equal to 2, and then my y will have to be negative 1. So one thing you can see that I can freely write down my x value. So I write down my x equal to 3. I can do that. But then you can see I cannot simply write down my y values. My y values will have to depend on the x value. So my y values actually have to be 1 minus x. It cannot be any other numbers. It have to be 1 minus x. So if my x is 3, so my y will be 1 minus 3, which is negative 2. So you can see right here, I can write anything I want. So I can choose my x equal to 4, but then this have to be minus 3. So this is the things that I can freely assign a number to it. So I can assign my x values to be 5. So here, however, my y cannot be any other numbers. It has to be 1 minus x. So it will be 1 minus 5. So it will have to be minus 4. So here, the numbers here that I can freely assign to is what we call a free variable. So we have a free variable here. We can set our x to be free. So we can set our x to be free, and then our y will have to depend on that free variable in the form of this is x, and then my y will be 1 minus x. So this notation here is saying that I can freely assign my x values to be any numbers, but then my y cannot be any numbers. It has to be related to that free variable in this particular way, right? So I can freely assign my x value, but then my y value will have to depend on that free variable in this sense. Your y will have to be 1 minus x. So we can write down our solution pair like this. X is equal to x. This is how we identify x is a free variable. Free variable meaning that I can freely assign any value to that variable, but then my y cannot be any numbers. It have to be 1 minus x. Okay, so there's no reason why your x has to be a free variable. We can also set up this table differently, like this. For example, this is my y, this is my x. I can choose my y equal to 0. I can choose my y equal to 1. So if I choose my y equal to 0, my x cannot be any other number. It has to be 1 minus y. So here has to be 1. If this is 1, this has to be 0. So if this is a 2, if my y is 2, my x here will have to be 1 minus y. So it have to be minus 1. If this is 3, this will be 1 minus 3, which is minus 2. So as you can see, there's no reason why we choose x to be a free variable. We can also choose y to be our free variable. So this is free variable. So I can assign any number to that. But immediately when you see that when we are doing y, we're using y, our free variable, our x cannot be any number. If this is 4, our x is restricted. It cannot be any number. It has to depend on this number in this way. It has to be 1 minus 4. So this gives us minus 3. So another way of writing the solution pair is to set our y to be the free variable, and then our x here will have to be in this form 1 minus y. So this is a concept of free variable. Right now, the concept of free variable is kind of pretty easy to see. But then in the next video, when we are dealing with the higher dimensions, which means when we have more equation and more unknown, the concept of free variable will appear in those sections. And this is something that you need to be aware of, because otherwise this is going to be a little bit strange. So free variable just simply the variables where we can freely assign a particular value to it. Okay, so when you see people writing out x equal to x, or people write down y equal to y, then you know that those are the free variable for the system. Okay, so let's quickly summarize. For the system of two equation and two unknown, there's only three possibility. As you can see, we either have a unique solutions, or we have no solutions, where we say the system is inconsistent, and we can have infinitely many solutions in a situation like this. So this is one major characteristic for solving system of linear equations. So in a system of solving system of linear equations, you have three possibilities. You either have a unique solution, or you have a no solutions, or you have infinitely many solutions. And this is true not only for a system of two equation and two unknown, but in general systems that looks like this, we will also have the same thing. We either have unique solutions, no solutions, or infinitely many solutions. We will never have a system of linear equation that have exactly 7 solutions. That's not possible. There's only 3 cases, which is unique solutions, okay, no solutions, and infinitely many solutions. So for the geometrical interpretations for a system of 2 equation and 2 unknown are pretty easy to see, because these are just straight line on your xy plane. However, if you have a system of 3 equation and 3 unknown, we can still do it. We can still represent them in the x, y, z plane. So if you have taken Calc 3, you know that x minus 2y plus 3z equal to 0 is a plane. So this is a plane. So this is equation of the plane. So it's the equation of the plane on the xyz if you're using the xyz coordinate system. So when you have a system of equations, 3 equation and 3 unknown, so you have planes on this 3-dimensional space, and the situation is slightly more complicated. It's harder to draw, but you can see from here, there's a possibility that we have 3 planes intersect at one point, so you have unique solutions. You can also have no solutions. The 3 planes are parallel, just like the parallel lines that we have we saw just now. And we can also have no solution because of situation that looks like this. The 3 planes looks like there are many ways that you can actually have no solutions, in the sense that you cannot find solutions that is common to both 3 planes. And there's also a possibility there's no solution right here. So this is the cases where there are no solutions. So the geometrical interpretation is a little bit more complex right now. But this is showing you the situations where the configuration of the plane where you would not be able to find a common point that is common to all these 3 planes. This is the unique solutions that we talk about, and this is infinitely many solutions. These are solutions are all lying right here. This is a case where you have infinitely many solutions. This is again the case where you have infinitely many solutions. So situations when we have more equations and more unknowns is going to be a little bit more complex. And we will not be obsessed about the geometrical interpretations when you have like 4 equations and 4 unknown, because that is a situation where you can't really draw anything. We can only deal with this is what we call R3, 3-dimensional space. This is the maximum we can go in terms of imagining it. So we will not be bothered with the geometrical interpretations for situation in 4-dimension and 5-dimensional space. But one thing for sure is that as long as the system is linear, then the solutions is only fall into that 3 categories, okay, no matter what. The 3 categories are the unique solutions, no solution, or infinitely many solutions. And we'll look at how we actually obtain solutions for a system that looks like this and system that is more complicated than this in the next video, in the next sections, which is on Gaussian eliminations. All right, I will see you then. And this will be the end of this particular discussion here. All right, that concludes our discussion on section 1.1. I'll see you in the next video. Have a good one.